Okay, now, if we look at this matrix A, we see no reason why we should expect that the first three rows should reduce to anything but an identity matrix. First three rows being a 3 by 3 matrix within the 5 by 3 matrix. This being real world data, we really don't expect the numbers to match up in such a way that any one of these rows would be a sum of multiples of the other two. Okay, that would be just kind of a special thing. These numbers are kind of big. They come from real world data. There's all kinds of uncertainties in the observation process, besides which this data basically being quadratic, it's even less likely to happen. I won't go into detail why that is, but if you think about the numbers, it's not that hard to understand. Okay, so what we have, and let me see if I'm getting the whole board here. Yeah, I think I am. Okay, what we have then is a matrix that we expect to reduce to this form. We expect the first three rows to reduce to the identity. Well, we have a 1 here, a 1 here, and a 1 here. Zeros everywhere else, so certainly we have the identity there. And once we have that, we understand from row reduction that the other two rows are going to get wiped out, give us nothing but zeros. So A reduces to this, meaning that A has a rank of 3. Now, A acts on vectors of length 3 because the rows have length 3. So A is acting on vectors from like R3. It has a rank of 3, so its null space has to have dimension 3. Its row space has dimension 3. Sorry. Its row space has dimension 3. Its null space has to have dimension 0. Okay? Its row space is just, well, spanned by these three vectors. Well, these three vectors are the standard basis of R3. So the row space is all of R3. And since this matrix acts on R3, it leaves nothing for the null space. Null space being the set of vectors that map to the 0 vector. Okay, now I just won't say it leaves nothing. It leaves the 0 vector because the 0 vector does always map to the 0 vector, but this gives us a null space of dimension 0. And then, of course, the column space has dimension 3. The column space, well, each leading one in the reduced matrix tells us a row or a column that we look at for the column space. Well, we have a leading one in each column. And a leading one, okay, there's a leading one. Each leading one here tells us that we get the corresponding columns. We get this column from this leading one, this column from this leading one, this column from this leading one, which means not this column of the original matrix. We've established this. It's the original. I'm getting words all messed up here. Okay? It's not the columns of this matrix. It's the columns of the original matrix. So this column, and this column of the original matrix form a basis for the column space. Now, this gives us a picture. Okay? We have V equals Rn, W equals Rm. I can't tell my M from an N there. Again, this is kind of a rough board. I'm going to retire this thing shortly, sand it down or something. In this case, of course, for this matrix, this is R3 and this is R5. So we'll just say, okay, this is R3. This is R5. The row space and the null space are orthogonal. Now, of course, the null space here is just the 0 vector. So you don't have the opportunity to have anything orthogonal. But in most cases, or in the general case, you have a row space and a null space. Their dimensions add up to the dimension of the space. There'll be n for the general situation, or 3 if we're talking about the transformation induced by this matrix. Okay, so we have a row space of A. So I designate that by the Greek letter rho of A. Okay, it's a Greek letter rho. It's not P, it's rho. Think about the rhyme, row, row, row your boat. If you read this as P, you get a completely different meaning. Now, row of A means the row space of A. That would be this one. It's spanned by these three vectors, these three rows. It's all of R3, it's the whole thing, but we're going to still represent it like this because it's the most general picture. Then, here we have the null space of A. Okay, here we have the column space. And every vector in this whole space here maps into this column space. This column space turns out to be the row space of A transpose for a very simple reason, because when you transpose a matrix, you switch its rows and its columns. So the row space of the transpose is the column space of the original matrix. And then you also have this thing here, because this column space, well, let's look at the dimensions. The dimension of this is 3. Okay? The dimension here is 0. Dimension of the null space is 0. The dimension of the column space is 3. This is a 5-dimensional space. So the dimension of your null space of A transpose, and let me digress just a little bit, any matrix that acts on a space splits the space into the row space of that matrix and the null space of that matrix. And these two are orthogonal, and we've verified that. Okay, we've verified it over here, but it works just as well over here. Okay, now over here, you have to apply the transpose to these vectors if you want to map them, and you're not going to really map them back to here, although you could, but that wouldn't be relevant. So just imagine you use the transpose to map this 5-dimensional space over to some other 3-dimensional space. In any case, you have your row space of A transpose, your null space of A transpose. Their dimensions have to add up to the dimension of the space, so this has to have dimension 2, because 3 and 2 gives you 5. The dimension of the whole space is 5. And also, the row space of any matrix is orthogonal to the null space of that matrix. These are very important properties, and they're properties that everybody in both courses should understand. Now, the way those properties are put together in order to get to this final result here is a little more subtle. It uses a little more information than we expect the Math 177 students to have, although some attended class might be able to do this and would be welcome to. Might be able to actually see where this all comes from. Okay, so there's our picture of our 4 fundamental subspaces. Okay, these are the 4 fundamental subspaces. Now, when I draw these subspaces, I'm assuming you have a transformation from this space to this space by this matrix, and the transformation is just defined that by the fact, or well, here's the definition of the transformation. Transformation applied to a vector V over here is what you get when you multiply this matrix by V. Okay? When you multiply this matrix by any vector in R3, you're going to get a vector in R5. So that's the basic, these are the 4 basic subspaces. Now say the 4 fundamental subspaces of the transformation defined by the matrix A.